Hello, students. This is going to be a very short video just to summarize the main points we are hoping you'll get out of the reading that we've provided and or the video with Neil deGrasse Tyson that we've posted as well about Big Bang Theory. So the reading I'm talking about is the section out of the textbook that is available online. You can either read it off your device, print it off, or you can listen to me reading it for you. I'm sorry about the video. Next time I'll actually have it shooting at the text instead of just the top of my head as I'm reading, because that's not very entertaining. There is a note sheet to accompany this video that you're watching right now. It's also available for you to either view on your device or print off. You do not have to take notes. You can just watch this video and summarize your thoughts. But I am going to use those notes to kind of guide this summary. Okay, so I'm just going to share that on the screen now so you can see what I mean. So here we go. All right. So for astronomy, there are three main points that we want to come across or get across, and that's that there's a Big Bang Theory, what it is and what evidence supports it, that the universe is changing and what evidence supports that, and astronomical data collection. And that's kind of an extension piece that we'll talk about later. So for this first main topic, Big Bang Theory, there are two pieces of evidence that supports Big Bang Theory. You can pause the video now and try to remember what they are if you have already watched the videos while I get stuff on here. All right, so the first piece of data is called red shift. Okay, so all galaxies give off light, and we can receive the light that they give off with our satellites and telescopes. And what we see is that the spectra of distant galaxies are red shifted, meaning that they are moving away from us. And it's kind of the same idea as dropping a rock in a puddle of water or a pool of water. The ripples in the water that are right where the rock went in are really close together. But then as it moves out, the ripples are further and further and further apart. So what redshift tells us is that these galaxies are moving further away each time we receive data. They're getting, those wavelengths are further and further apart. So the redshift happens when they have longer wavelengths. Which the word wavelengths is very long and my writing on this thing is very bad. So I'm going to use this lovely symbol to represent wavelengths. So they're longer wavelengths, which means that these galaxies are, most of them are moving away from us. If they're moving away from us, that means that the universe must be expanding. Okay, so the redshift supports Big Bang Theory because Big Bang is all about this one point in time where everything began and it exploded outwards. And if it's exploding outward, everything is getting further and further away, and it's expanding, it's spreading out. So the universe is expanding. It's not staying the same size, it's not getting smaller, it's expanding. All right, so they also found that if they can figured out the velocity of galaxies moving away is directly proportional to the distance from Earth. So if it's twice as far away, it's got twice the velocity. And they were able to plot this data, and they found that it was a constant, and they call this Hubble's constant. And the important part about this is that once they realized that it was all in relation, they can track it back and extrapolate backwards to find out at what point in time did this all begin. And they found out that because if something is expanding, it must have at one point in time started somewhere, right? And so they found with their data that they estimated the universe expansion began 13.8 billion years ago. So began 13.8 billion years ago, or if you're a lazy scientist like myself, BYA. All right, so they don't know what caused this moment of singularity to all of a sudden explode outwards. They don't know what event caused the beginning, and they don't know what came before the beginning. They being we, us, no, we don't know. There's lots of theories, of course. One of my favorite theories is that's the other end of a black hole, and that everything is actually a multiverse, but we'll talk about that later. But we don't for sure know, we don't have any data for that. It's all supposition at this moment, as far as I'm aware, not an astrophysicist. So maybe I'm not in the loop as much as other people. Okay. So the second piece of data is, who remembers it? It's cosmic background. Ooh, no, that's not what I want to do. Cosmic background radiation. I practiced this so much and it's not working. So, oh well. Background radiation. All right, so cosmic background radiation and wavelengths are kind of go hand in hand. So this universe began at something very hot and dense and then exploded outwards. So it started with very short wavelengths, which is associated with very hot radiation, specifically gamma rays. And then as everything began to expand and as the wavelengths began to spread apart and get longer, everything began to cool as well. So we should expect to see with our data that the universe is cooling and contract that over time. And with these, with our technology, we have found exactly that the universe is very slowly cooling, because as the wavelengths spread out, the more heat escapes and it becomes cooler. So at the beginning, it was very hot, and we had short wavelengths, which are associated with gamma rays. And now, as it's expanding, it's cooler. We have longer wavelengths. That's not longer, it's longer wavelengths. And we're now in the cooler section of the electromagnetic spectrum. So we're in the more microwave emission of radiation. And that Kobe and DubMap false colored, you can't see me pointing, but the two pictures at the bottom show the cooling down over time. Okay, so as the wavelengths stretch, radiation changes and the universe cools down. So those are our two pieces of evidence that support Big Bang Theory, because of course, if it wasn't expanding, if it was staying the same, it would stay the same temperature, or if it was getting smaller, you would think it would be getting more dense and more hotter, but it's not. It's doing exactly what we think it is with expansion. Thank you very much for joining us. Please let us know if you have any questions. I hope you're all doing well, and we will talk soon.